Well, good morning, fourth graders. It's me again, Mr. Martins, and I have to tell you, I'm feeling a little excited. If Unit 4 was a marathon, and let me tell you, there have been times where it's felt a little bit like a marathon, and we've just been running and running and running and running without a break. However, if it were a marathon, this would be the home stretch, which means we are almost at the end. And I have some good news. This big idea that we're about to get started is going to be a little bit more familiar to most of you and will be a nice break to what we've been doing. And then when we get to the end, we'll go back and review as we will be getting ready for the test soon. So, big idea number 4 is analyzing patterns. And as we talk about analyzing patterns, let's take a look at our two learning targets. The first one says, I can find and list factor pairs and list multiples. I hope that sounds familiar to everybody because we've done this. I know we did this before, and I know we've talked about this in between. So, listing factor pairs and listing multiples, both things we've done. The second learning target, I can recognize factors and multiples and use them to generate patterns. As we're thinking about those learning targets, I also want you thinking about where you fit along this learning scale. Are you a 1? Both learning targets I've mentioned don't sound familiar. Are you a 2? Sounds familiar, but you feel like you're going to need a lot of help before you get it. 3, familiar, you get it, but you know you're going to need a little bit of practice to get into the routine? Or are you feeling like you're a 4, you're ready for a challenge, you can teach others? Hopefully, there are a couple of you out there. We might need some help. Uh, we might need some help getting some students on board with what we're doing. All right, so let's go ahead and jump in. I've broken this lesson into activities. First activity says find factor pairs for the given numbers. So here's some practice with finding factor pairs. The direction says list all the factor pairs for each number, and uh, I want to circle the word all. So when we're talking about factor pairs, there is such a thing as listing all the factor pairs. And I say that because later on we'll be looking at multiples, and multiples can go on for a long time, if not, actually, multiples can go on forever. And so I would never ask you to do all of something that would go on forever, right? Okay, so factor pairs, list all of them. Here we go. The first one that I'm going to recommend that you always record first is 1 times and then the number. So that is our first factor pair, 1 times 32. You see, factors are numbers you multiply. So that's what we're looking for, numbers you multiply to get to 32. And I like to go in order. So I've used up 1. The next number after 1 is 2. Is 2 a factor of 32? Now, before you're quick to say yes or no, there are some tricks that I use, and here's the one for 2. If the number ends in 0, 2, 4, 6, or 8, so basically even numbers, 2 is a factor. So 2 is a factor of 32. And if you wanted to, you could count by 2's to get to 32. Or you could divide 32 divided by 2 to find out the missing number. That would look like this: 32 divided by 2. 2 goes in the 3 one time. 1 times 2 is 2. Bring down that 2. And then 2 goes in the 12 6 times. And so it's 2 times 16 that would get you 32. And then I would check 3, and I know that 3 times 10 is 30, and 3 times 11 is 33, and so there is no 3 for a factor of 32. Then I would check 4, and I would do the same thing. I know that 4 times um, 4 times 7 is 28, and 4 times 8 is 32, and so there I go, 4 times 8. Then I would check for 5, and once again, I told you I would give you tricks. Before you go deciding yes or no, the trick for 5 is if the number ends in 0 or 5, 5 is a factor, and 32 does not. Then I would check 6, and there's a trick for 6. And the trick goes if 2 is a factor and 3 is a factor, 6 is always a factor. That's one for you to remember. And as you can see, 2 is a factor, but 3 is not a factor. And both of them would have to be factors for 6 to be factors. And you could also check. So if my tricks are confusing, you can just ask yourself, is there a number times 6 that equals 32? Well, I know 6 times 5 is 30, and 6 times 6 is 36, and so there is no 6 for 32. Then I would check 7, and I would do the same thing. 7 times 4 is 28. 7 times 5 is 35. There is no 7 that works for 32. 8 we've already used. 9, there is a trick for 9. I'm not going to quite get to the trick for 9 yet. I'm saving that for the next one. What you could do is you can ask yourself, like, can you think of a number times 9 that equals 32? And the answer is no to that. And once you've checked all the single digits, 1 through 9, then you're done. And so 32 has 3 factor pairs, or 6 factors: 1, 32, 2, 16, 4, and 8. And we've done our job with 32. If you're feeling like you want to do some practice on your own, you want to hit the pause button on this one, feel free to do that. Otherwise, we're going to do the same thing together. So we're going to start with 1 times 63, and then we're going to move on to 2. Is 2 a factor of 63? Let's use that trick. For 2 to be a factor of 63, 63 would have to end in an even number, and it doesn't. So 2 is not a factor. Now we're getting to 3, and I want to show you that there's a trick for 3 that we haven't talked about. And the trick goes, and hopefully you've noticed that for each of the numbers, the tricks have been a little bit different. And so this one is a little bit different too. The trick goes, if the sum of the digits is divisible by 3, then the number is divisible by 3. And what that means, and I want to remind you that this only works for 3, or this variant only works for 3. What that means is if you add 6 plus 3, and you would get 9, and 3 is a factor of 9, the number that you get, then 3 is a factor of 63. So 6 plus 3 is 9, and 3 is a factor of 9, so 3 is a factor of 63. Now, if that's confusing to you, that's okay. Then try the long method, which actually is not so long because you guys are like professional at division right now. We can go ahead and divide 63 by 3. 3 goes into 6 2 times. Bring down that 3. 3 goes into 3 one time. And there's no remainder. That's what we're looking for. No remainder. And so we get 3 and 21. So we'll say 3 times 21. 3 times 21 equals 63, and there's no remainder. For 4, we would have to check 4. and we would have to use some division. So I'm going to make some space over here. Wish my eraser was bigger. I'm sure there is a bigger eraser, but I don't know how to use it. So that's what I got going on there. So we would do 63 divided by 4. 4 goes into 6 one time. Again, I call this the long way, but you guys are like division experts now. So it's not too long. Okay, you see that remainder there? That means that 4 is not a factor of 63. We can see that it goes in 15 times, but not 15 even times without a remainder. So 4 is not a factor. 5 is not a factor. How did I know so quickly? Well, it doesn't end in 0 or 5. 5 is a factor of numbers that end in 0 or 5. Don't believe me? Start counting by fives, and you'll find out quickly that anytime that you skip count by 5, the number will end in either 0 or 5. Now, is 6 a factor? Remember what I told you, for 6 to be a factor, 2 and 3 must be a factor. In this case, we have 3, but no 2, so 6 is not a factor. 7, we would have to check. There's no rule or trick for 7, except I know that 7 times, let's see, 7 times 8 is 56, and 7 times 9 is 63. So we would have a 7 times 9 there. 7 times 9 is 63. 7 times 10 is 70. So that's just 7 more from 63. I'm just checking to make sure I got that right. Let's see, for 8, no, 8's not going to work because 8 times 8 is 64. So that jumps right over 63. And oh, the trick for 9. Well, we already have 9 there, but I was going to tell you that this trick that we have for 3 also works with 9, and you're doing the same thing. So if the sum of the digits, which would be 6 plus 3 equals 9, if the sum of all digits, which is 9, is also divisible by 9, then 63 is divisible by 9. And since 9 is a factor of 9, it works. Again, guys, if that part is confusing, then remember, you can always just use division like we've done over here. Or did do over here, and I erased it. I don't know why I erased it when I said that. Okay, so those are all of our single digits. And so the factor pairs of 63 are 1 times 63, 3 times 21, and 7 times 9, 3 different pairs of numbers. Okay, so maybe, just maybe, you hit the pause button on that one and you did some of that on your own. Maybe you didn't hit the pause button and do some of that on your own. If that's the case, we have 3 more examples. I'm just going to keep on rolling, but at some point, if you feel like, oh, I want to do some of this on my own, then you hit that pause button and you do some of this on your own. If you feel like you need the help the rest of the way, then that's fine too. Here I go. 44. We have 1 times 44, because 1 is a factor of every single number. Then I'm going to check 2. Since 44 ends in an even number, 2 is a factor, and I just happen to know that it's 22, because 2 times 22 is 44. Is 3 a factor? Well, let's see. And this trick only works for 3. 4 plus 4 is 8. And 3 is not a factor of 8. So 3 is not a factor of 44. Then I check 4, and I already have, no, I don't have 4 already there. 4 times 11 would equal 44. 5 is not a factor because 44 ends in 4. 6 is not a factor because I have 2 but no 3. 7 is not a factor because 7 times 6 is 42, and 7 times 7 is 49, so we skip right over that. And 8 is not a factor because 8 times 5 is 40, and 8 times 6 is 48, so we skip right over it. And 9 is not a factor because 4 plus 4 is 8, and 9 is not a factor of 8. And so there we have it. Those are our 3 pairs of factors for 44. It's almost sounding like I'm trying to convince you that there are always 3 pairs of factors, and that is not true. It just happens to be a coincidence that the first 3 numbers have 3 pairs of factors. But let's see what happens on the next one. All right, so first of all, we have 1 times 29. Now we're going to check 2, and 2 is not a factor because 29 does not end in an even number. Then we'll check 3. 2 plus 9 is 11. 3 is not a factor of 11, so it doesn't work for 29. Again, you can always check that. You can always ask yourself, 3 times 10 is 30. That's close, but that goes over. And 3 times 9 is 27. That's under, so that's not going to work. Then I checked 4. 4 is not going to work. 4 times 7 is 28. That's as close as I'll get. 5 won't work because it doesn't end in a 0 or 5. 6 won't work because 2 is not a factor and 3 is not a factor. And we know that 6 times 5 is 30, and that's as close as we'll get. 7 won't work. 8 doesn't work. 9 doesn't work. And once you've checked all the single digits, you can stop right there and look at that. We only have one factor pair for 29. We only have 1 times 29. So I wanted to demonstrate to you guys that it's not always 3 pairs of factors. It all depends on the number. Obviously, some of the bigger numbers are going to have a lot more factor pairs. All right, moving on to 35. If you haven't already hit that pause button to try it on your own, I'd really like to encourage you to do it on this one. So before I get started, hit that pause button, try some of this on your own. Hopefully you're coming back. Here's what I have. 35, we have 1 times 35. Always start with 1. 1 is always a factor. Will 2 work? No, it won't. And hopefully you were thinking because 5 is not an even number. Will 3 work? Hopefully you were thinking 3 doesn't work because 3 times 11 is 33. 3 times 12 is 36. We skip right over 35. That's not going to work. Or if you remember the trick, 3 plus 5 is 8. 3 is not a factor of 8. So now we move on to 4. 4 is not going to work either. 4 times 8 is 32. 4 times 9 is 36. We skip right over 35. Now we check 5, and oh, why, yes, it ends in a 5. I was going to say even number. We're checking 5. 35 ends in 5, and so 5 times 7 equals 35. Very good. Then we check 8, then we check 9, and we come to realize that 35 has 2 factor pairs, 1 times 35 and 5 times 7. Remember, you're not always looking for a certain number of factor pairs because each number has its own pair of factor pairs. We have some numbers like 29 that have just 1 pair of factor pairs, and we have some numbers like 35 that has 2 factor pairs, and then others that have 3. Each number has its. All right, so that's the end of that activity. So hopefully by now you've come back to the work we've done with factor pairs. And if you're wondering, Mr. Martins, I really would like a list of all those tricks. Ta-da! They're right there. They're right there. So at some point on your own, if you'd like to copy those down, they're going to be in this slideshow. And I don't know if Mr. Waltz and Mrs. Potts have done this with their class, but I've put our entire math slideshow, Unit 4 math slideshow into our Google Classroom. So it's something that you can request that they do for you. I can easily give them access. But or you can go ahead and hit the pause button and record all these down. These are the factor tricks. These are all the ones that I've used. Um, so 2 is a factor if the number ends in an even number. 3 is a factor if the sum of all digits is divisible by 3. 4 is a factor if the last 2 digits is divisible by 4. 5 is a factor if the number ends in 0 or 5. 6 is a factor if the number is divisible by 2 and 3. And 3. 8 is a factor if the last 3 digits is divisible by 8. And 9 is a factor if the sum of all digits is divisible by 9. So remember, these are tricks. These are not things that you have to use. You can always just go back and do it the old-fashioned long way and divide to find out. Basically, you're looking for numbers with no dividers or no remainders. Okay, so that's the end of activity 1. I feel like this is taking a long time. Many of you don't know this, but Mrs. Koberstein challenged me to keep these videos at about 20 minutes long. And some of my videos were more like 50 minutes long. The more recent ones have been like 26, 27, close to 30. So I feel good about that. I feel good about that. I think this one is going to push it because there are so many different activities and lessons as a part of this one. So don't blame me. I didn't write the curriculum. Activity 2 is determine whether a number is prime or composite. Well, I have to tell you guys, we've already looked at composite and prime numbers in activity 1. Now I'm just going to show you what we did and how to determine whether it's prime or composite. And almost every single number is either prime or composite, except for the number 1. The number 1 is neither prime or composite, and we're just not going to get into why. We're just going to hold on to that, put a pin in it, and at some point in your life, you'll figure out why. So a number greater than 1 that has 1 and itself as its only factor pair is considered a prime number. Some prime numbers are like 2, 5, 3, 23, and we can add one that we figured out, 29. And the reason we can add 29 is because in activity 1, we learned that the only factor pair for 29 was 1 times 29. That's what makes it prime. The only factor pair for 2 is 1 times 2. The only factor pair for 5 is 1 times 5. The only factor pair for 11 is 1 times 11. The only factor pair for 23 is 1 times 23. That's what makes those numbers prime numbers. All other numbers greater than 1 that have multiple factor pairs are considered composite numbers. So we have numbers like 4, 12, 25, 100, and the other numbers we've explored, like 44 and 35. They've had more than one factor pair, and so we call them composite numbers. I don't have a trick for remembering the difference between prime and composite, so it's just going to have to be something that you work on. One idea that I just had now is the word prime almost sounds special, superior, prime. Maybe I'm getting that from Transformers, Optimus Prime. Well, prime numbers are special numbers. Um, most numbers have more than one factor pair to them. Prime numbers are special in the fact that they only have one factor pair. And if we were to start listing prime numbers, guys, early on in the smaller numbers, it seems like there are a whole bunch. But then you get to a point where there could be like hundreds of numbers between hundreds of composite numbers before you get to the next prime number. And there are students in college that spend years just studying prime numbers. It's incredible. That's not something I would do. But maybe somebody in our class is interested in that. I don't know. Okay, so hopefully you understand what a prime number is. Let's get into some activity to decide whether or not numbers are prime or composite. Okay, let me erase this here. Okay, so it says to decide whether or not the number is a prime or composite. And remember, prime sounds special. And prime numbers are special because they only have one factor pair, which is 1 times itself. So maybe that's how we'll remember prime. All right, so looking at the number 45, we have 1 times 45. Now, if that was it, 45 would be prime, but it's not it. We know that 5 times 9 is 45. And there could even be more, but that wouldn't matter because this extra one already proves that 45 is composite. And I'm going to allow you to use the letter C for composite. Um, or if you want to, you can write it out. It's up to you. Looking at 31, we have 1 times 31. Now, if that were the only factor pair, that would mean it would be prime, but let's find out for sure. So is 2 a factor? Nope, 31 doesn't end in an even number. Is 3 a factor? Nope, 3 times 9 is 27, 3 times 10 is 30, 3 times 11 is 33. 3 is not a factor. Or if you want to use a trick, 3 plus 1 is 4. 3 is not a factor of 4. Is 4 a factor? Nope. 4 times 7 is 28. 4 times 8 is 32. We go right past that. Is 5 a factor? Nope. It does not end in 0 or 5. Is 6 a factor? Nope. 2 and 3 are not factors. Is 7 a factor? Nope. 7 times 4 is 28. 7 times 5 is 35. 8 is not a factor. 9 is not a factor. And so 1 times 31 is its only factor pair, meaning this number is prime or a prime number. It's special. It only has one factor pair. And believe me, guys, that does make that number special. All right, looking at 81, some students last year said, oh, 81 looks like 31. That means it's prime. No, that's not a rule. That's not a rule. It's not something I ever said. We got to make sure, guys. All right, so we have 1 times 81. If that is its only factor pair, that makes it prime. But let's check it out. Is 2 a factor? Nope, doesn't end in an even number. Is 3 a factor? I hear a lot of you quickly saying no, because 81 is not typically a number you attach to 3. But wait a second, let's check it out. What is 8 plus 1? 9. Is 3 a factor of 9? Yes. So 81 and 3 do go together. I'm going to prove it to you. 3 goes into 8 2 times. Some of you already see it. 3 goes into 21 7 times. And there is no remainder. And that's what I was looking for. In other words, you can say 3 times 27 equals 81. And I can go on. In fact, some of you already noticed that 9 times 9 is 81. And so that makes 81, what is it? Is it prime or is it composite? Is it special or is it not? It's not very special. No, most numbers have multiple factor pairs. So we're going to say that 81 is composite. All right, looking at 57. Some student last year thought, oh, well, you know what, Mr. Martins, I figured something out. If it's an odd number, then it's prime. What are you talking about? If it's an odd number, it's prime. 45 is an odd number. 45 is not prime. Please don't make up silly things. Let's stick with rules that work. And the rule that we're going to use is that we've got to check and make sure. So, first of all, we have 1 times 57. That's what we have first. If we stop there, it's prime. If we can think of more factor pairs, then it's composite. So let's check 2. Is 2 a factor? No, you're right. It doesn't end in an even number. How about 3? Is 3 a factor? Don't be so quick to decide. You can either decide with division or you can use our trick. 5 plus 7 is 12. Is 3 a factor of 12? Why, yes, it is. So let's check and make sure. I'm going to prove it to you right here. 3 goes into 5 one time. 3 goes into 27 9 times. And there it is, no remainder. So 3 times 19. 3 times 19. You want to know what? I actually pulled this example from our book. And our book in the answer key said that 57 was prime. I can't believe they got that wrong. But I will tell you what else. I had a fourth grader, I think 2 or 3 years ago, that figured this out. Now I could have figured it out as well, but silly me, sometimes I just go along with the answer key, but not anymore. Not anymore. It feels pretty wonderful when you can prove the answer key wrong. Okay, so we have 3 times 19. We could continue to check, but once we get into more than one factor pair, we've already learned that 57 is composite. Because the direction says the direction doesn't say to list all the factor pairs. It's just to decide whether or not it's prime or composite. So once we get to our decision, once we prove our decision, then we can move on. Okay, so hopefully that made sense. If it did not, you are more than welcome to rewind, pause, hit it again. But that is the end of the prime and composite lesson. And as I move on, I believe to the final activity. Yep, activity 3. I'm feeling like I'm over time here, but I don't see a counter. I really should start a timer for myself when I'm doing these lessons. But we're going to keep going because this is the last activity. Activity 3 says recognize factors and multiples and use them to generate patterns. So here's that learning target that most of you probably said that you needed the most help with because it didn't sound familiar. So the directions say use the rule to complete the pattern. So the first one says if the rule is skip count by 11, then continue the pattern. 11, 22. What are we doing? We're adding 11. 33. Keep adding 11. 44, 55, 66, 77, 88, 99. So there is our skip counting by 11. So hopefully you guys have seen that this is a piece of cake. You get this. Next one says skip count by 9. And so that's kind of like listing multiples of 9. So we have 9, which is 9 times 1, and then 18, which is 9 times 2, then 27, which is 9 times 3, then 9 times 4, 36, 9 times 5, 45, 9 times 6, 54, 9 times 7, 63, 9 times 8, 72, 9 times 9, 81, 9 times 10, 90. We've skip counted by nines. Again, same thing as listing multiples. Listing multiples is when you start with like 9 times 1, and then 9 times 2, and then 9 times 3, and then 9 times 4. And for multiples, it's very possible to go on for a long time. There's no end to multiples. All right, last one is skip count by 8, which is multiples of 8. We have 8 times 1, 8 times 2, 8 times 3, 8 times 4 would be 32, 8 times 5 would be 40, 8 times 6 would be 48, 8 times 7 would be 56, 8 times 8, 8 times 9, 8 times 10 would be 80. And there you have it. That's the end of activity 3. I'm just about to find out how long this lesson took. Oh, yeah, that's it, because the next one is lesson 11. So hopefully you guys understood that lesson. If you didn't, once again, please feel free to go back and watch it again. Rewind, pause, speed it up, slow it down, whatever you need to do to increase your learning through these slides. That's the end.